The title of my slide or talk is not there. Is here. And I will be talking about synthesis in general. My background is in organic synthesis, synthetic organic chemistry, and I got my training originally in alkaline chemistry, natural product chemistry, and then I did a postdoc at Berkeley with one of the pioneers of asymmetric synthesis, Henry Rappaport. And since then, since mid-80s, that's what I have been trying to do, trying to understand the sort of nuances, the small energy differences between different transition states leading to enantiomeric or stereochemically highly defined end products. That's very important, as you know, for pharmaceuticals. It's getting more and more important also for agricultural chemistry and so on and so on. Today I will not talk about asymmetric synthesis, although that's sort of my hay. I will be talking about synthesis in general, because developing asymmetric synthesis requires also the development of methodology, and you will see a lot of that going on. When Bob asked me to give this talk, he suggested that I would talk about click chemistry. I will talk about click chemistry, but not only click chemistry. We will start from the 17th century, and we will go from there, because I'm a great fan of history, and in order for one to know where to go, you have to know your backgrounds. And I will not stop with click chemistry, because click chemistry already got a Nobel Prize last year. So we will go beyond that also towards the end of my talk. But let's go and look at what people have said about synthesis in general in terms of chemistry. Before chemistry, as we know, chemistry was known. I've taken a passage from Boyle's The Skeptical Chemist book, which is available to everybody to read nowadays thanks to the Gutenberg program. And he actually talks about, not in terms of synthesis per se, but he talks about the work of a chemist or alchemist, I guess, in those days, as there may be more elements than 5 or 6, so we didn't have 118 then yet. So the elements of one body may be different from those of another, whence it would follow that from the resolution of decompound body there may result mixtures of an altogether new kind by the coalition of elements that never perhaps convened before. I think that's basically what we talk about when we talk about synthetic chemistry, where we make compounds that have not been there before. And that's going to be a very, very crucial point in the when we talk about click chemistry. Then we'll follow a little bit of what went on. Chemistry itself didn't exist as chemistry before about mid-18th century, when this guy Delius took up a post at Erlangen, and he was so disliked by his faculty friends that they actually gave him basically a broom closet underneath the staircase and said, well, you go there and you do your stinking stuff over there. And he nailed a plaque saying Chemie, Laboratorium für Chemie. And that's the first time that is known that anybody has used chemistry per se in an academic setting. So we're talking about 2.5 centuries ago, not that long ago. Then we go to Cambridge. The fourth BP 1702 professor was John Hadley, and he talked about chemistry as the art of separating bodies into their simplest constituent parts, of uniting these parts again and reproducing the original compound, and also by different mixtures and various methods of combining bodies to produce new substances which exist not in nature. And that again is the sort of, you can see the elements of purely synthetic world there where we're coming, but this is mid-18th century. But the ideas were there already then. Lavoisier, one can never jump over Antoine. Chemistry is the science of analysis. Now comes the analysis, and we're talking about late 18th century. So the analysis of what we have been doing, or what a chemist has been doing, takes a prominent role in the works of chemists. By consulting chemical systems, it will be found that this science of chemical analysis has made rapid progress in our times. So analysis preceded synthesis. We have to know what we do so that we know what we do. Blank? No. A couple of quotations. Michael Faraday, whom we know from candles and electricity and so on, he was a chemist also, and you will see in a few slides a little bit more about it. Chemistry is necessarily an experimental science. Very true, very true. David Reed in 1833, there is no more eminently practical science than chemistry. So again, the value of practice and the value of lab work comes into play. And the first usage of synthetical experiments in the context of organic chemistry comes from Hofmann, the German who went to England and started many, many wonderful things in England, including the Royal Society. It was first used by Mosprat and Hofmann in 1843. And the French Berthelot, having completed his analytical work, the chemist proposes to recompose what he has destroyed. He takes as his point of departure the ultimate of analysis, that is, simple bodies, and he compels them to unite with each other, and by their combination to reform the same natural principles which constitute all material beings. Such is the object of chemical synthesis. And now we're beginning to be very close to what the synthesis in modern usage is. Benzoylfest was held in Berlin in 1890, and Kekulé said there that he who aspires to be a scientist must study the works of the greatest researchers so thoroughly that he is able not only to read between the lines, but even to develop the ability to divine unexpressed thoughts. So creative mind becomes again in the central focus of chemical research. And then we go to the actual chemistry. The first synthesis, or what we would say preparations maybe, the first that I have found to be documented was by the Swedish Carl Scheele, the preparation of prussic acid already in 1783. And that can be considered to be an organic compound because it's a compound of carbon, hydrogen, and like my postdoc supervisor said that a truly organic compound has to have at least one nitrogen atom also. So it's a simple compound, HCN. Wöhler made oxalic acid from cyanide in 1824. 1824, Leopold Kmeli prepared an organic acid, crocinic acid in 1824, and then I think this is an extremely important thing. A truly remarkable organic synthesis was developed by Henry Hennell and Michael Faraday in 1825. Hydration of alkene. And his work was basically this. Henry Hennell performed the reaction on the left by taking ethylene as gas and then reacting that with sulfuric acid, and he got a salt of something. And that was the sodium sulfate salt of ethanol. Faraday didn't have the analytical powers to measure what that was, so he said to Henry Hennell, why don't you go to France and talk to this guy, there's the man Berthelot, he has all the analytical means, so he could take a look at that. He came here to France, in Paris. They realized that the compound was truly the sulfate, and they hydrolyzed the sulfate and obtained ethanol. The first synthesis of an organic compound, synthetic organic compound, I would say. Now, what's remarkable about this is that Shell developed the industrial process that is still being used for the industrial production of ethanol in 1947 by taking ethylene gas and hydrating that with a phosphoric acid catalyst at high temperature and high pressures. And this is the process that is being used even today to produce about 850,000 tons of synthetic ethanol annually. So it's basically utilizing the same principle that was used in the first organic synthesis, as I would recall. Now, many people say that the first organic synthesis was Wöhler's synthesis of urea, but that came only a couple of years later. And Wöhler's reasoning was not to make organic compounds, but it was something totally different. As you can see from his letter to his teacher Berzelius, that he was so happy that he was able to make a compound that exists in living nature out of non-living nature materials. So that was basically a death blow to the vis vitalis, the life's force concept. Not the first synthesis of an organic compound, but of course equally important in those days. A couple of other syntheses that were rather interesting and by today's methodologies rather simple, and one wouldn't do anything like this anymore except maybe industry in some chemically less developed countries, if I may say so. So from charcoal you can make carbon disulfide, and carbon disulfide you can, after the oxidation, you can transform that to a carbon tet, and then dimerize that to a tetrachloroethylene, and under sunlight you can convert that to a trichloroacetic acid. Hans Kolbe, famous for electrolysis reactions and utilizing electrons, already in mid-19th century, so almost 200 years ago, electrosynthesis was very important. It was developing then. And he was able to make acetic acid, and that's one of the sort of seminal synthesis of developing organic chemistry in those days. Organic zinc reagents became very early on. Already in 1850, Edward Franklin synthesized diethyl zinc, a notorious compound that we know that is highly explosive and very, very easily oxidized by air, reacts with oxygen. Edward Franklin made half a kilo of it. If I would ask my students, any of my students, to make half a kilo of distilled diethyl zinc, I don't think anybody would make it anymore. And then Alexander Butlerov from Kazan, University of Kazan, he developed the first practical use of organic zinc or any organometallic compounds in the synthesis of carbon-carbon bonds by taking acetyl chloride and dimethyl zinc, an even more hazardous chemical, and he prepared T-butanol. And that was at the University of Kazan, where I think Kevin Lamb from UC Louvain went. So the birth of synthesis features a lot of chemists. There we see Wöhler, we see Kolbe, we see William Perkin by making cinnamic acid early on. The industrial chemistry was born basically by Carl Grebe and Carl Liebermann in 1869 when they prepared synthetic alizarin as a synthetic dye, and that basically started the industrial dye production. The chemical industry was basically born thereabouts. Also Adolf von Baeyer, by synthesizing indigo, played a very important role there. And I mentioned earlier the uses of synthetic experiments. The word synthesis itself was used by Hermann Kolbe. just a couple of years later after Hoffman. And a few other names which one simply cannot just walk over from the history. Marcel Berthelot, who said famously that chemistry creates its own object. In other words, we chemists, by the force of synthesis, we can create the objects that we study. If we want to study some phenomena, some physical properties and so on, we can create the chemicals that can be used to study those. And that's very important for the click chemistry, as you will see in a moment. And then Bob Woodward from Harvard, the master of organic synthesis, who got a Nobel Prize for the development of art of organic synthesis. He said, maybe this is the most important thing here, is that there is excitement, adventure and challenge, and there can be a great art in organic synthesis. And that is true, especially when you look at the development of synthesis that went on. I'll have to take Gustav Kompa here also, because I come from Aalto University. It's on the top right corner, the Aalto University, which is the new name for the old Helsinki University of Technology. And we have the beautiful insignia here on the top left-hand side, which was developed by Eliel Saarinen, one of the famous Finnish architects. And it was approved by the government of Finland in 1939, just before the Second World War. When Aalto University was formed, obviously they couldn't use an insignia that was developed and designed by an architect named Saarinen, because it's the Aalto University, and Aalto is the other famous Finnish architect. So they designed a new insignia, and I think the one on the left is much more beautiful. Gustav Kompa was the first professor of Helsinki University of Technology, and he was actually a professor already before Helsinki University of Technology became a university. He was one of the 12 founding professors of the Helsinki University of Technology. They were numbered in those days. Number 1 was theoretical mathematics, number 2 was theoretical physics, number 3 was applied mathematics, and number 4 was chemistry. And Gustav Kompa was the number 4 chemist, or number 4 professor. And since then, even today, even though we are called Aalto University, organic chemistry has its code is Chem 4 to commemorate Gustav Kompa. Gustav Kompa, he made the first total synthesis of what E.J. Corey, another Nobel laureate, has said, the first total synthesis of a complex natural product, that was camphor, which contains only 2 stereocenters in the molecule, but it was an important compound. In 1904, camphor was utilized for instance, in the production of gunpowder, to sort of modulate the reactivity of gunpowder. And in 1904, that was important because there was the Russian-Japan war going on. And camphor was basically gotten from Korea, from the camphor trees. So it was basically blocked because Korea was owned by Japan, and because Japan was in war with Russia, we in Western countries, we didn't have access to camphor. So there was no production of gunpowder. And early 20th century, as you know, the whole world was basically just a boiling kettle. So everybody needed gunpowder. So there was a huge drive for development of synthesis of camphor. Kompa did it in 1904, but very soon after that, the German company Schering utilized the synthesis developed by Marcel and Berthelot, where they utilized pinene as the starting material and some fancy organometallic transformations to convert that to camphor, and they started large-scale industrial productions. Compa founded the synthesis, organic synthesis and natural product synthesis in Finland, and in his inauguration speech for the Helsinki University of Technology, he stressed that chemistry must be practical. That's exactly what Barry Sharpless said, for instance, in his Nobel lecture last year. Chemistry must be practical. But it has to be strongly curiosity-driven at the same time. It has to be industrially applicable. And again, all these sentiments were said by Barry last year in Sweden. Being industrially applicable, the synthesis has to be robust. It has to be scalable, so that you can scale it up or you can scale it out. In other words, you can use parallel reactions, for instance, at the same time, producing several batches at the same time, simultaneously. It has to be useful and meaningful. There has to be a good reason for making compounds, but still strongly curiosity-driven. Generality of reactions, target diversity, another term that we started using in the 1990s, diversity in chemistry and biology. Economies, they came later on. We will say a few words about economies. So that means that basically the organic synthesis already then started to shift towards not only making compounds, but also developing methodology, because now we were at the stage that we needed the methods to make the compounds. We had the elements of analysis, we had very crude elements of making compounds, but we needed new methodologies. And again, that required new analytical methods later on. So 1940s, 1950s, we saw the development of chromatographies, different spectroscopies, starting from UV, IR, later mass spec and NMR, for instance. They came sort of because we needed them to analyze the products of synthesis, different kinds of methodologies. And then a statement which was launched in 2003, the 100th anniversary of Compass camphor synthesis in Finland, where we came to the conclusion that the state of the art of organic synthesis is defined by the complexity of the targets that can be attacked successfully. And to students, I always say that science is basically about making the impossible possible. So where are we? We're roughly about 1980s, 1990s here. Where was organic chemistry, organic synthesis then? It had developed from urea, and it had gone through these developments. There's the structure of camphor for you. Then 1951, Carl Gerasi developed the synthesis of norethindrone, the first steroid hormone, synthetic steroid hormone. And then things went on. Erythromycin was synthesized by Woodward in 1979, and then the so far most complex compound that has been synthesized by man was by Yoshito Kishi from Harvard, again by synthesis of halitoxin. And on this slide I have the sort of complexity evolution, how much compounds have evolved, and I've used just one measure of complexity, and because I was an asymmetric synthetic chemist, and I was looking at the stereocenters, so I took the number of stereocenters in a given molecule. The first compound, 1828, no stereocenters. 1868, alizarin, no stereocenters. 1903, one independent stereocenter. 1954, strychnine by Woodward, contained 6 stereocenters. Erythromycin, 1979, about 20 stereocenters, and then in 1994, palitoxin, a humongously complex natural product that was synthesized by total synthesis. It contained 63 independent stereocenters. Now, when I showed this to my students in the late 1990s, I said that if you look at all these developments, And then you continue here. It's an exponential growth, basically. So when you go from 1994 to 2020, for instance, the students should be able to make compounds that contain easily a couple of hundred stereocenters. Nobody has been able to develop anything even close to palitroxine. So for some reason in mid-1990s, something stopped. The search for complex target compounds ended. And why was that? That was because of the development of molecular biology, the thing that people started to talk about, individual medicine, development of drug compounds and therapies that are based on chemicals. The pharmaceutical companies needed new compounds faster and faster and faster. They didn't want more complex compounds. They just wanted anything that would be okay. And mid-90s, that was when combinatorial chemistry was basically born. I remember when I was visiting Merck Sharp&Dome in England, and Ray Baker asked me, so what do you think about combinatorial chemistry? I said to him that, well, it's fun, but it takes the dressing out of synthesis, because nowadays we were doing synthesis on pins, then 96 well plates and so on. And I said to Ray Baker, but as an industrial chemist, what do you think about it? And Ray turned around, grinned, and said, it's good for us synthetic organic chemists, because all the CombiChem people, they make all these compounds. They make hundreds and hundreds and thousands and tens of thousands of compounds which they screen, and it means that then we have to make bigger batches so that they can subject the compounds to more biological evaluations. And that's where you need synthetic organic chemistry. But the fact is that the focus of synthetic organic chemistry changed. We needed fast methods. We needed methods which are really, truly robust. Methods where we can quickly develop reliable syntheses of huge libraries of compounds. The biggest libraries that I know of that were developed in the 1990s were already compound libraries which contained something on the order of tens of thousands of compounds. Then, today, they tell me that a good industrial CombiChem chemist can produce easily 13,000 compounds per week. Now, if that's the case, then let's look at the reasons for synthesis. Recap up to here now. In the early 19th century, I think the most important thing definitely was Wöhler. Disprove vital force, because that changed chemistry altogether. The development of chemical analysis, definitely important. Late 19th century, synthesis proper, for instance, the industrial synthesis of alizarin and the birth of all these big pharmaceutical and chemical companies, BASF, Agfa, and so on. Early 20th century, proof of structures became very important, because we didn't have NMR yet, we didn't have X-ray yet. So by chemical synthesis you could prove the structure of a natural product that you had isolated. So that was basically analysis. The birth of big pharma came around then also. And as an anecdote, again, I've mentioned acetic acid earlier. Acetic acid played a very prominent role there, because in the late 19th century, early 20th century, people at Bayer developed a very robust method of acetylating phenols. Now everybody knows aspirin. That was the second painkiller Bayer developed. The first painkiller they developed was an acetylation product of a phenol also, which they proposed that it's much better than aspirin, because this new compound does not produce as strong an acid in your stomach, and and gastric ulcer and so on. And it is definitely not addictive. So let's promote that before aspirin. And that compound was heroin. Not addictive. Wheels could have turned differently, I think. Late 20th century, we saw that biologically active compounds, drugs, natural products, and so on, they became the central focus of organic synthesis. New materials, very important, the development of new materials, because that way we can develop new properties. Industrial materials, nanotechnology was basically born because of the facilitating role of synthesis, organic synthesis and inorganic synthesis at the same time. Inorganic and organic started to sort of come together again in the late 70s, I would say, maybe late 1980s, when organic chemists and inorganic chemists refound each other again. And then you can see all these things. The combinatorial chemistry was born, then microwaves came in, organic catalysis came in, and the seeds of flow reactions came in the late 20th century. Now, everybody knows the 4 steps quickly destroy efficiency. If you have a long synthesis and 15 steps is not long, 15 chemical steps is nowadays it's rather common in the synthesis of drug compounds, for instance. But if your chemical yield in each reaction is only about like 80%, you don't perform a 15-step synthesis because it's not practical anymore. So the robustness again comes into play here. About those, at about that time, step economy became very important. The overall efficiency, the overall yield of a chemical synthesis rapidly diminishes, the number of chemical steps or synthetic steps increases, and therefore things that are obvious nowadays is that convergent synthesis is much more efficient than a linear synthetic scheme. In other words, you start from like branches and you culminate them and you make more and more advanced intermediates, which you then combine together to form even more complex products. Barry Trost gave us the concept of atom economy, very important when people were talking about reaction yields beforehand, which is basically just the actual quantity of products achieved divided by the theoretical quantity of products that could be achieved. It doesn't take into account what happens to the starting materials. Chemical engineers started talking about reaction selectivity, very important in catalysis. How selective is a reaction towards a particular product? And then Barry Trost came back and he said that when you think about the economy of a synthesis, you should really think about how much waste you produce, how much of the atoms is actually converted into the usable products. And this is something that we are nowadays extremely aware because of the fact that we realize that with our growing number of people in the world and growing technologies, and we are developing more and more of waste products. And that is something we just cannot tolerate anymore. So to put this back together again, if the early stages were about target-oriented synthesis, as we call them, we had a natural products or designed molecules, material sciences, biologically interesting or theoretically interesting compounds. Those were the ones where you know what you want to make exactly, and you strive for that. Then 1960s methods-oriented synthesis, synthetic methodology. In 1960s we started seeing the chemical reagents, new reagents that allowed us to make hydride reductions and different kinds of catalytic processes and so on. Synthetic strategies, the methods of analyzing synthesis, and synthetic tactics, they come from there. 1990s, diversity-oriented synthesis, when we realized that we need to have a breadth of compounds that we can make. People started making drug libraries, for instance, and catalyst libraries, so that you can screen many things. And again, analysis was important there, because we had the means of analyzing thousands and thousands of reaction products easily. And then towards the end of the last millennium, people started to realize that we chemists, we don't make only compounds, we actually make properties, function-oriented synthesis. We can design a property for something, and then we can design a compound that has those properties, because we could, for instance, organic leads were basically born because we understood the homo-lumo concepts of the different organic dyes much better, and we could fine-tune the homo-lumo gap, in other words, the absorption area of a compound very easily. And if we can define that, then we can design a compound, and then the computer guy gives the chemical structure to a synthetic chemist, and the synthetic chemist hits his head against the wall and eventually produces the compound after many attempts. Now, then we go back to history again. Now we start talking about clicking here. The first click reactions, as we know them today, come from late 19th century. Buchner reacted diazoacetate with double bonds. And the top reaction is the way he described the chemical reaction initially. And the bottom one is the one that he used actually, and that's the reaction that he is written in modern language. So it's basically a dipolar cycloaddition of a diazoacetate onto an electron-deficient double bond, which produces a 5-membered ring, two new bonds basically there, the carbon-carbon bond and the carbon-nitrogen bond. Arthur Michael developed another interesting reaction, and this is the way he described the reaction in the journal Practical Chemistry. Phenylazide reacting with a acetylenic compound without catalyst produced a new compound that he drew like this. Now, these are the notations that were used in the 1890s. Nowadays we would draw a triple bond here, and phenylazide we would just draw a linear N3 here. But that was the first use of an azide-acetylene cycloaddition reaction. Things were sort of slow to develop, and in the 1950s, Aalto developed a reaction of a strained double bond together with an azide, phenylazide, which is here. And a couple of years later, another Nobel laureate, Ziegler, from Ziegler-Natta reaction, he reacted a norbornene with a high-energy double bond with an azide to produce a compound like this. Now, these reactions are not regiospecific. So if you had an unsymmetrical starting material, you would get a mixture of products. And that's important for the later developments. Aalto and Ziegler's work led to this man, Rolf Huysen, to start studying dipolar cycloadditions in the 1950s, 1960s, and he looked at the reactions, categorized them, and studied the mechanisms and scope of several different dipolar cycloaddition reactions. And he came to the conclusion that the dream of reactions proceeding quantitatively under mild conditions without the need of catalysis is often fulfilled by concerted cycloadditions. True enough, provided that there is at least one of the starting materials is a high energy compound that wants to basically react very easily. But acetylenes per se are not those kinds of compounds. So they needed some persuasion. And then we come to Sharpless. Sharpless has just gotten his first Nobel Prize. When they started, they wrote a review with Mike Finn and Hans Kolb about what they call click chemistry, which is a set of powerful selective and modular blocks that work reliably in both small and large-scale applications. And they identified certain reactions that are very useful in click chemistry. Cycloadditions of unsaturated species, and here you can see the 1,3 dipolar cycloaddition reactions were their favorite ones. Diels-Alder transformations in one form or another would also be favored. Some nucleophilic substitution reactions, especially ring opening reactions of straight heterocyclic electrophiles. That's basically because they had developed earlier methodologies for making epoxides and aziridines from unsaturated compounds. And then breaking the 3-membered rings is something that is energetically favorable. Carbonyl chemistry of the non-aldol type, that I guess in those days everybody had to say aldol at some stage. And another reaction that Sharpless had also already been working on was the addition reactions to carbon-carbon multiple bonds, especially oxidative cases. That was basically because they had Sharpless's first Nobel Prize was basically on the development of dihydroxylation reactions of double bonds, but also Michael additions of nucleophilic reagents. They enumerated a number of suitable click-type reactions, and what is required of the click-type reactions, the reactions should be modular and wide in scope. Back to basically what Kompo was saying. They should operate under very simple reaction conditions and give very high yields. Obvious. They should take place in no solvent or a solvent that is benign or easily removed. At some point, Sharpless was toying of the idea, because he was already at Scripps then, he was toying with the idea that maybe one could use seawater as the solvent for reactions. They should only generate inoffensive byproducts that can be removed by non-chromatographic methods, and they should be stereospecific, not necessarily enantioselective, and be highly selective for a single product. So the dichotomy between regiochemistry should be somehow eliminated. And then the final thing, which I think this is almost repeating the high yields, they should have a high thermodynamic driving force, usually greater than 20 kilocalories per mole, and proceed rapidly to completion. That means high yield, basically. So that was 2001. Very soon they realized that unsymmetrical acetylenes give mixtures of products, and they were usually 1-to-1 mixtures of regioisomeric products. At the same time, Morten Meldal from Denmark realized that these reactions can actually be catalyzed with copper. Copper as a soft Lewis acid will bind to a triple bond and will activate the triple bond. The mechanism was not fully understood in those days yet, but it soon became clear what the mechanism is. Meldal used copper 1. Now, copper 1 is a rather tricky copper species to handle in laboratory, and especially in large quantities. And Valeri Fokin in Sharpless's group realized that if you take copper 2 and throw in a little bit of reducing agent, like sodium ascorbate, you actually make copper 1 in situ. And in those cases, both Meldal and Sharpless obtained a single product from a terminal acetylene in reaction with an azide. And they called, or this reaction became known as the copper-mediated azide acetylene cycloaddition, copper AAC. The mechanism has been studied, and here's a presentation by Henk Hiemstra from Holland, where you can see that the activation basically starts from coordination of the dimeric copper species with a triple bond. Then you have basically, with a base, you remove the acetylenic hydrogen, which now becomes more acidic because of the activation by Lewis acid, and you form an organocopper species. Then it undergoes something, and this is something that in 2006 people believed that this is something that's just a metal cycle as an intermediate. It's a little bit more complicated than this. So this became the click reaction. The click reaction where an organic azide with a terminal alkyne with a copper catalyst gives you a 1,4 disubstituted triazole. Barry Sharpless, Morten Meldal, Rolf Huysend, and then an important lady here, Caroline Bertozzi, who took up this chemistry and started developing something that she called bioorthogonal reactions, which are reactions of functional groups that are so selected for each other that they can be ligated in a richly functionalized biological milieu. In other words, in a living system, in a living cell, maybe even in a living animal, or, as they have recently proven, in a living human being. Just a few cases where I think this was one of the first types of reactions they utilized was a modified Staudinger reaction where they took a mannosamines, which are converted in cells. These are converted into sialic acids and incorporated as sialic acid derivatives. They are incorporated into the glycans on cell surfaces. If you have in the R group, if you have an azide, then you can use this azide to do the click reaction with something which has, for instance, a dye, and they utilize that to show the distribution of different glycosylated members on normal cells versus cancerous cells, etc., etc. They developed many different ways of utilizing reactions, because copper was not, although we can eat copper and we contain copper, but copper is not good. You can't put too much of copper to a living cell because it'll die. So that's not a particularly wise idea. So they started looking at other ways of reacting alkenes. And they went back to the Ziegler case, where in the Ziegler case, if you remember, we had the norbornene double bond, which is a strain double bond. If you put the strain into a triple bond, like put it in a ring, 8-membered ring, or even better, in a 7-membered ring, then you accelerate the reactions, and they have produced methodologies of doing the click reactions up to 4,000 times faster than with a copper catalyst. And that means that you can do them in a living cell to monitor things in real time, what's happening in cells, or on cells, basically, I would say. So the popular click reactions are the Sharpless Meldal copper AAC, the strain promoted AAC by Bertozzi, and the inverse electron demand Diels-Alder reaction, which was also developed by Bertozzi originally. Now we come into some more recent things. Those were about 20 years ago, those developments, about half an hour. Jeff Bode realized that you can actually build molecules that contain a bulvaline. Bulvaline is a compound that is a shape-shifting compound. So, in other words, if you have a bulvaline which has a couple of attachments on it, it's not a single compound, but it can take up several different configurations. In fact, you can calculate that there would be, for basic bulvaline itself, there would be more than 1 million different identities of it. When you have a di-substituted compound, they came to a realization that if you put, for instance, a boronic acid, 2 boronic acids into a bulvaline, and then you put a carbon-13 label on it, then it undergoes these isomerizations, and for this doubly substituted compound, they calculated that there will be 860 possible isomers. Then they threw in sialic acid. Sialic acid binds to these boronic acids in 2 different ways, basically. And basically what you see is when you take a C13 NMR spectrum, you have a barcode of the 2 different compounds, or 2 different barcodes. And you can analyze the products like that. That I already said. Then other people started looking at it again, and they analyzed the number of isomers, and they came to the conclusion that indeed there are several different configurations and isomers of the compounds, but there are actually only 6 different, chemically different, distinct isomers: A, B, C, D, E, and F. And there are enantiomers of F, B, and C. So in other words, there are basically 9 different compounds, but 6 individual compounds. Now, this was John Moses' research work. Development of antibiotics is an important thing. And for the longest time, we had a very, very powerful antibiotic, vancomycin, and its analogs. They bind to what is known as lipid 2, and the binding to the lipid 2 is rather well understood nowadays, how it occurs. But the fact is that there are a number of multi-drug resistant bacteria that have developed resistance to vancomycin also. Moses' group realized that if they actually dimerize the vancomycin and put a shape-shifting core, a la Jeffrey Bode, and use click chemistry to bind 2 vancomycin warheads onto it, they will have, at any given point of time, they will have a number of different compounds that are there, and the bacterium cannot develop resistance to all of the isomers. This is really recent work, about a couple of weeks ago, in proceedings of the National Academy of Science. But they have shown that the strains that they have studied do not develop resistance. Whether this will become the sort of next step in the development of antibiotics or not, nobody knows, but definitely it again proves that the click chemistry has given us very important tools. Besides that, Carolyn Bertossi's group has been involved in developing targeted compounds that can be, warheads can be clicked onto a monoclonal antibodies targeted towards cancer cells. So you can put in a highly specific chemo agent that will only bind to cancer cells. Whether that's the next step, nobody knows, but again, a very important development. Just a few more slides here towards the end. Back to Norris Award lecturer George Hammond, the Hammond postulate person, and he was also the man who is considered to be the father of photochemistry. He said in 1968 that the most fundamental and lasting objective of synthesis is not the production of new compounds, but the production of properties. And that's definitely what click chemistry has given us. Economies are important. Recently we are talking about other economies, Reinhard Hoffman and Phil Barron launched the idea of redox economies. Why bother going up in oxidation levels and down, reducing the compounds on the synthetic scheme, if we can retain the same oxidation level or go towards one direction only. Very important, because that eliminates unnecessary chemical steps. And then economies of time. Yuhiro Hayashi has written 2 very good review articles about time economy, and I take just one example of another Rappaport student, Tim Jamieson from MIT, who published nearly 10 years ago a flow reaction for the synthesis of ibuprofen in 3 minutes in flow reaction, where in one flow reactor they can produce 8 grams per hour. But flow reactors are basically, they are HPLC tubes. And instead of having one HPLC tube, you can stack them together like 500 tubes together. So you can scale out the reaction. And you can, with 500 HPLC tubes and a number of pumps, you can produce 500 times that, you can produce 4 kilos of ibuprofen in 3 minutes. Any pharmaceutical person would like to have one of those on their summer cottage or whatever. To finish up tomorrow, my crystal ball is over there. Function-oriented synthesis has come and it stays here, thanks to combinatorial chemistry and thanks to click chemistry. The next stage, I would, from my crystal ball, I would say that the next stage is that we would start looking at polymers made out of functional monomers, so that the monomer itself has functions, has some properties. It can be light absorbing, it can be whatever, greasy molecule that recognizes other molecules and so on. And then we can basically build like Lego bricks, we can build cities out of them, Lego cities. Energy efficiency, that's definitely there. Electrosynthesis was developed 150 years ago, more than that, but still very, very few laboratories have the means of using electrosynthesis in practical ways. Light, definitely, the ultimate reducing power is sunlight. Why don't we use it? We can use, and thanks to LED technologies, it can be used in wonderful ways. We developed a synthesis where we used blue LED lights to catalyze radical reactions of iodine and sulfur compounds without any side products in a very, very fast reaction. And that's being used by a Finnish paper company, actually. Can't tell you where they use it, but it's interesting. This is something where we have to go sustainable, renewable, or recyclable starting materials. We don't have enough atoms in the whole universe to make everything. So we have to be able to recycle. How about using our polyethylenes, our polypropylenes to make ethylene and propylene? Time pot economies, these will require new things. Benign oxidation reduction technologies, definitely. Here, for instance, the oxidation technology, a stunning realization is that current production of nylon utilizes oxidation of ketone alcohol. It's a mixture of cyclohexanone into adipic acid. And that is being done utilizing nitric acid-based oxidants. As a side product, we get nitrogen oxides. About 12% of man-made nitrogen oxides up in the air comes from nylon production. That's amazing. Definitely what we need is new bond-forming reactions, new ways of building up any bonds, carbon-carbon, carbon heteroatom, metal-carbon bonds, etc. understanding directing forces, theoretical chemistry, it will never go away, and these are the important recent developments. Flow chemistry came here, you saw an example of flow chemistry. Robotics, artificial intelligence, again, Tim Jamison's laboratory came out with a very, very wonderful development of artificial intelligence to optimize chemical reactions in flow. That came out a couple of years ago in Science. So we are living very, very exciting times, I think. That's where we should be going and clicking away. Thank you.
Very stimulating lecture. I'm sure there are some questions in the audience. You want to think about it. Do you think click chemistry is going to take the fun out of organic synthesis?
No. Quite the contrary, it opens up new avenues. We have a number, basically 3 very powerful click reactions that are being used at the moment. The copper AG, the SPAC, and the inverse electron demand desolver. But we need more.
Yeah. So there's plenty of room for people to develop new methodologies.
Yeah.
Okay. Yes.
So in that click chemistry, making that heterocyclic ring, are there any functionalities that would disallow that from happening? Could you put anything on that azide to functionalize another material, or are there some functionalities that are essentially incompatible?
You cannot have sort of contradicting functionality. So if you have, for instance, an acetylene and a strain double bond, then you're in trouble. Or if you have a phosphine in the molecule, then you're running the problem of getting a Staudinger reaction or an acetylene to get the dipolar cycloaddition. So yes, definitely there are limitations, but these are rather robust technologies, I would say. Free hydroxy groups are tolerated, free alcohols are okay. You can run the reactions like Bertozzi, their group are running these reactions in zebrafish or mice, so it's in water, basically. No problem with that. They don't have to dilute the zebrafish with DMSO.
What about isocyanate groups?
Sorry?
Isocyanate groups, NCO.
Probably.
Okay.
First, this morning chose well the place of sitting under the Finnish flag.
I can tell that our colleague is also from the Scandinavian country, from Sweden.
But also a question. You talked much about synthesis to use to make pharmaceutical products, but at the end you mentioned nylon, but has it been used for complex plastics as well to reach higher temperatures or make stronger plastics?
Glad you asked that. Sharpless talked about click chemistry in his Nobel Prize lecture in 2001. And they had already published the first review article in click chemistry. Last year, well, it was actually 2014, when I heard Sharpless give a talk about what they called SUFEX reaction, sulfur fluoride exchange reaction, where you basically make what he was saying is that for polymers you have phosphate groups, and DNA is chiral not because of the chiral sugar, but because the chiral sugar imposes chirality on the phosphate. and the phosphates are causing the helicity. Now you can replace a phosphate with its close analog, a sulfate, and if you put into the sulfate a fluorine atom, which is quite stable there, it doesn't get hydrolyzed, just like an organic acyl fluoride is okay. You can throw it into water and it doesn't do anything there. The sulfur fluoride does the same thing. It's stable, but it's structurally similar to phosphate, and that imposes helicity into the whatever you make. So what they did was that they took bisphenol A basically and put a couple of sulfates on it, and then they took another one where they took a phenol and a TMS protected phenol, and they coupled them together with a proper catalyst. You get an instantaneous reaction. You get polymers of molecular weight about 500,000. The polymer dispersity about 1.1 to 1.5, so highly dispersed polymer, and they have produced kilos of these polymers by clicking. So definitely yes, and they have shown that these compounds, these polymers, they can be woven into materials. Of course, it's bisphenol A, so that's something that we have to look at again. So how do we replace that? But still, the methodology is there, and he talked about this in his last year's Nobel Prize talk. Whether he's going to get a third Nobel Prize for that, nobody knows.
Thank you.
If he wants to get another Nobel Prize, he has to get a move on. He's now over 80. Other questions? No? Sudden silence. Well, I think in that case we will thank you once again, and it wouldn't be appropriate to come to a meeting like this without giving you something to take away. This is something you will appreciate, I know, from experience. And let me, on behalf of all of the audience, thank you once again for your talk, very stimulating.